Alright, be prepared today because we are going to do a little bit of math today. So what we want to do is calculate the electric potential from the electric field. And if it's a constant electric field, it's really easy. We already saw it's just E, negative EX, basically. But what if it's not a constant electric field? What if the electric field changes with X or changes with R? So if we've used Gauss's law or integration to determine the electric field from a distribution of charges, it's possible to calculate the electric potential caused by that distribution of charges as well at various locations. Remember that electric potential is generally defined as zero at a point infinitely far from the distribution of charges. So we're going to start first of all with kind of the simplest example, and this comes from Gauss's law, a spherical conductor of radius r and a net charge q, and I want to determine the function for the electric potential in terms of q, r, and any fundamental constants for this situation. And so there's really two different regions that we're interested in. One is outside the conductor and one is inside the conductor. The thing to point out about a spherical conductor or conducting object is that all the charge sits on the outside surface of that object. So we're going to figure out both the electric field outside the conductor and inside the conductor using Gauss's law. And if you remember, this is a pretty easy situation. We'd use a spherical Gaussian surface, which has a surface area of 4 pi r squared. Outside the conductor, you've enclosed all the charge Q in the conductor, and so you get E equals 1 over 4 pi epsilon naught Q times r squared. Looks like a point charge at the center of the sphere. Shouldn't be a shock to you at this point. Inside the conductor, also pretty easy. If you're inside the conductor, all of the charge is outside of your surface, your Gaussian surface, so you've enclosed zero charge, so the electric field happens to be zero inside the conductor. So let's look at electric potential, and we're going to calculate potential for both these locations, and the way I'm going to do it is by using the expression negative dV over dr equals electric field, which means V at point B minus V at point A is equal to negative integrated from RA to RB E dot dr. So the first one that I'm going to do is I'm going to do this one here, and we'll do this integration and I'm trying to make sure I didn't flip my signs. No, I didn't flip my signs. I did fine. Okay, so we start at infinity, and so we'll integrate from r to infinity. I'm just double checking that my signs are right. Okay, yep, I'm cool. So here would be my change in voltage from infinity to point R, and so I'm going point R to infinity. That negative sign, what that would ultimately do is kind of flip these around a little bit. The thing about the potential at infinity is we define it as zero. If I insert all of this stuff in here, we would end up with this as my final result. Double check, negative R, negatives cancel, yep, we're good. So we are good. So you'd end up with this voltage at any point outside the conductor. It really looks like the potential from a point charge. Inside the conductor, things get a little bit funny because, well, we're looking at from the surface of the conductor to point R. So we're starting from the outside and working our way in, and really the outside of the inside of the conductor is at radius r. Well, there is a potential there. It's equal to 1 over 4 pi epsilon naught q over big R. So what would end up happening here, this whole side becomes 0, because the integral of 0 is 0. So V at any point inside the conductor is equal to V at the outside of the conductor, and so we get that you have a constant potential inside the conductor. So while the electric field is 0, you can still have an electric potential that's not 0. It's just constant, which makes sense if we think about electric field as the change in electric potential. If there's 0 electric field, there's no change in electric potential, and so whatever the potential is at any one location has to be the same as the potential at other locations. Now I picked a second problem, which is I would consider to be a fairly difficult problem. And part A of this, calculate the electric field, not that bad. Part B of this one, find the electric potential, kind of ugly. So we have a spherical conducting shell with an inner radius of B and an outer radius of C placed concentrically around a spherical ball with a net charge of plus Q. And it's a, I didn't make it conducting, but it is a conducting spherical ball. And radius A. I want to determine the electric potential at the following locations. Electric field and potential at the following locations. Any point outside both these spherical shells, any point inside the outer spherical shell, any point in between the spherical shells, and any point inside the two spheres. So we'll start with points outside the spherical shell. The thing to point out about outside the spherical shell is if it's a spherical conductor, something interesting happens. And what's interesting that happens is charging by induction. The inside surface of this conductor gets a charge of negative Q, and the outside surface gets a charge of positive Q. Basically, this conducting spherical shell inside pulls the negative charges closer and pushes the positive charges outward. That doesn't really make all that much of a difference for us here. What's going to happen if we do our Q enclosed? We're still going to get positive Q because Q minus Q plus Q is still Q. And so we get our familiar electric field. Looks like if this is just a single sphere with positive Q. Not all that exciting. Our electric potential is also not all that exciting. It's really the exact same as the last problem. And the exact same process. Start from infinity, go to Q, or go to point R, which is some point outside the sphere. So, now let's look at inside that pink conductor. The one thing to point out about the Q enclosed, if you draw a Gaussian surface inside here, is the Q enclosed is negative Q plus Q, or 0. There's no electric field inside that conductor. What that should mean, and what should tell us, is that the electric potential is constant. Should be equal to V at point C, which is 1 over 4 pi epsilon naught Q over C. Now here's the interesting one, I think. Inside the two spheres, the electric field isn't too bad because the Q enclosed is just Q, and really it looks like as if the outer spherical conductor or the outer conducting surface didn't even exist. But the electric potential does look a little bit funny. The outer surface of this region is at B. Well, we know V of B and V of C are the same, so we can plug V of C in here, and we'll integrate that to R. And so what will happen is we'll get all of this stuff, which is really equal to this here when we integrate that. And then we add that to the other side, and so we actually get something that looks like this as your electric potential. Funny, huh? Now if we look inside the inside spherical conductor, really no shocks. Electric field should be constant, 0. And so V of A, which really should be V of this inside region, plug A in for R, and so this is the potential inside that outermost or that innermost conductor, and it's constant. So you kind of get this weird chaining thing that happens. If we were to graph these, what you'd see with electric field is that at 0 you get a spike, goes back to 0, you get another spike, and then out. With electric potential, what you'd see is it kind of goes like this, kind of stays constant, kind of goes like this, then stays constant. And we'll look at some of those types of graphs when we actually start to play around with some of these problems. So those are some ways to calculate electric potentials. We'll do some more practice of this in class with some other situations and look at what are some common situations you come across.